Every time you expose a new microservice in Kubernetes using a standard load balancer service, your cloud provider provisions a brand new static public IP address, and they charge you for every single one of them. Relying on those basic services also means relying on simple round-robin routing. You miss out on critical traffic controls like domain-based routing, sticky sessions, and native HTTPS encryption. Kubernetes Ingress solves this by providing a single consolidated entry point. Instead of paying for hundreds of individual load balancers, you funnel all cluster traffic through one IP address. In this tutorial, we will deploy an NGINX Ingress controller, establish a host-based routing rule, and configure secure network traffic. Mastering this entry point allows you to replace individual public load balancers with a centralized system that manages security and routing for the entire cluster. Left. Standard load balancers assign billable IPs to every service. Right. Ingress funnels all requests into one IP. This traffic cop applies strict logic, like whitelists and path-based routing. It uses two components, the Ingress resource rules and the Ingress controller engine. By separating the routing instructions from the processing engine, developers can continually write complex traffic logic for new applications without triggering a new paid load balancer from the cloud provider. In this Ingress configuration file, we define a host-based routing rule by specifying our test domain, foo.bar.com, mapping it to an existing internal backend service. We apply this file to our cluster using the standard Kubernetes apply command, and then check its status using Kubernetes get ingress. Looking at the terminal output, notice the space right beneath the address column header. It is entirely blank. That blank space proves our routing rules exist in a vacuum. We created the Ingress resource, but there is no active engine installed in the cluster to read or execute those instructions. A YAML manifest is completely inert until you deploy an active running infrastructure component configured to listen for it. To provide that engine locally, we deploy the NGINX Ingress controller. In MiniKube, this is done simply by running MiniKube add-ons enable ingress. Checking the pod logs shows exactly what we need. The NGINX engine actively detected our new ingress resource and successfully synced the foo.bar.com routing rule. Running the kube control get ingress command a second time confirms it. The previously empty address field is now populated with an active IP. Even with the controller running, there is a local environment limitation to handle. A standard web browser has no way to resolve our custom foo.bar.com test domain to this specific MiniKube IP address. This text file is our system's local DNS map. Adding this line to the /etc/hosts file forces the machine to route requests for our test domain directly to the MiniKube cluster IP. Taking the time to bridge this DNS gap locally allows you to fully test and validate your routing architecture on your own machine before pushing it to a live cloud environment. With the DNS mapped, we run a simple curl command, or open a browser, and navigate to foo.bar.com. The internal application responds successfully. The traffic flowed from the browser into our single ingress entry point and directly to the correct backend pod. This map shows horizontal scaling. Using path-based routing, the IP reads the URL slug, like /app1, and splits traffic to different backend services. The controller also supports TLS termination. A certificate secret allows it to natively handle HTTPS encryption right at the network edge. Instead of configuring security and routing logic across dozens of individual application pods, you offload all of that overhead onto a single, specialized gateway. With the controller active and the hosts mapped, you've established a consolidated traffic flow, allowing your machine to resolve custom domains to internal services without the cost of extra cloud IPs. Try expanding this configuration on your own. Deploy a second backend service and write a path-based rule to reach it, or generate a local TLS certificate to secure the connection. Managing this routing layer is the first step toward graduating from simple container testing to the architectural standards used in high-traffic deployments. Let us know in the comments if you successfully reached your internal service, and subscribe for the next DevOps tutorial.